All right, Calculus BC students, this is Mr. DeRozier, and over the course of the next couple of days, I'm going to film 6 different videos, one for each of the 6 questions that appeared on the 2019 BC exam. This is the exam that students would have taken in May. This first question is question number 1. That means it is a calculator active question. And we're going to go through this. I'll talk to you about how you would have earned some points. This is calculator active, so make sure you have your calculator handy. And let's get rocking and rolling. Okay, we're told that fish enter a lake at a rate modeled by the function e, given by e of t is equal to 20 plus 15 sine pi t over 6. Fish leave the lake at a rate modeled by the function L, given by L of t equals 4 plus 2 to the 0.1 t squared power. Both E of t and L of t are measured in fish per hour, and t is measured in hours since midnight. So just got a lot of information there. E of t is the rate that fish enter. So, okay, we've got that. Fish are leaving the lake by L of t, so this is my leaving. Think about the swimming pool problems that we've talked about. We talk about those as like the in and out problems. So the enter, this is the rate that fish are coming in. The L of t is the rate that fish are leaving or getting out. And t is hours measured since midnight. Okay. Part A, how many fish enter the lake over the 5-hour period from t equals 0 to 5 a.m.? Give your answer to the nearest whole number. Okay, well, I can tell you that in advance of filming, I already went on to my computer and I entered the 2 different functions. In part A, we want to know, part A, how many fish enter the lake over the 5-hour period? Well, E of t is the rate. It's how fast they enter. So how many enter? Well, that's going to be the integral from 0 to 5 of E of t dt. Let's switch on over to my computer. And here we go. I've put E of t, that's f1 of x, that's the blue graph. L of t, that's f2 of x, that's the red graph. And so I'm going to go over onto my screen and I'm going to go to Menu, Calculus, Numerical Integral. I'm integrating from 0 to 5. I'm integrating the enter function, E of t, so in this case f1 of x dx. I'm going to hit enter and I'm getting 153.458. Let's go back to my paper, back to the paper. So the integral from 0 to 5 of E of t dt is approximately 153.458. Now that's a great answer, except for the fact that they told you explicitly that they want you to, what do they want? Give your answer to the nearest whole number. So to the nearest whole number, that's going to be 153 fish. This is a 2-point problem. 1 point for having the correct integral, the integral from 0 to 5, E of t dt. 1 point for the correct answer expressed to the nearest whole number, for a grand total of 2 points. I would assume that for most of you that is a pretty straightforward computation. Keep in mind that this is calculator active. I want you to use your calculator all of the time. I do not want you to say, oh gosh, what's the integral of 20 plus 15 sine pi t over 6? Yeah, you better know how to do those things, but that's not the skill being assessed here. All right, let's, excuse me. Let's keep going. Let's look at part B. In part B, what is the average number of fish that leave the lake over the 5-hour period from midnight t equals 0 to 5 a.m.? Average number of fish, I think we know how to do that, and if not, we'll talk about that in a second, that are leaving the lake, so this is that L of t function, on the time period t equals 0 to t equals 5. Well, in calculus, The way that you find the average value of a function is you're going to use the formula 1 over b minus a, the integral from a to b of f of x dx. That's the formula that you need. That's not going to earn you any points here, but that's the formula. So what we need is going to be 1 over 5 minus 0, the integral from 0 to 5 of L of t dt. We're going to go over to the computer. We're going to go evaluate that integral. Here we go. So 1/5 times the integral, numerical integral, from 0 to 5. L of x is f2 of x, so f2 of x dx. And I'm getting 6.059. Let's go back and write that down. The integral, the average value is, what do we say? 6.059. 1 point for the integral, 1 point for the numerical answer. Do not round in this case. They didn't tell you to round, so we're not going to round. We're going to stick with the convention that answers will always be accurate to 3 places after the decimal, unless you are told otherwise. So that's A and B, and again, I would expect that these are high-scoring, sort of expected questions for you all. Let's look at part C. In part C, at what time for 0 less than or equal to t less than or equal to 8 is the greatest number of fish in the lake? This greatest number is an absolute max. Absolute max kind of question. So those are always a little tricky. We're going to have to look for our internal candidates. We're going to evaluate at our endpoints. We've got a lot of work to do here. So let's see where we are. And for that, I want to go back to the graph. Okay. Remember, my blue graph is f1 of x. That's the rate that fish are entering the lake. My red graph is the rate at which fish are leaving the lake. And so I can see here at the very beginning, say at time t equals 0, if I compare the red graph and the blue graph is taller than the red graph. So that means that the rate that fish are entering the lake is greater than the rate that fish are leaving the lake. And so in that case, at time t equals 0, the number of fish in the lake is going to be increasing. If I go out a little bit further, imagine a vertical line drawn here. The blue graph is taller than, has a y value that is greater than the red graph. So the number of fish in the lake is still increasing over here. But once I get past this intersection point, the red graph has the greater value than the blue graph. So fish are leaving the lake faster than they're entering. So in this case, the number of fish is decreasing. Well, you probably know what we're going to do. We're going to identify our candidate, which is the intersection point, because that's when the number of fish changes from increasing to decreasing. So let's do that. We're going to menu, analyze graph, intersection point. The intersection is at 6.203. That x value I'm going to save, so I'm going to highlight. I'm going to go to var, store var, and I'm going to call it A. I like to do that. And on my paper, I'm going to write down that A is 6.203. Let's go back to the paper. So for part C, at A, which is approximately 6.203, the number of fish in the lake changes from increasing to decreasing because the difference, E of t minus L of t, changes from positive to negative. There's a lot of other ways that you could express this. You could say E of t minus L of t is positive. Until we get to A, negative. Once we leave A, lots of reasons there. What I know is that A is a candidate for an absolute max. Absolute max number of fish. Well, that's the candidate. I also have to consider t equals 0 and t equals 8 are the endpoints. So what we're going to do is we're going to look at time t equals a, t equals 0, t equals 8. Now I'd like to say let's look at the number of fish that are in the lake at each of these 3 times, but the problem is they didn't actually give me a starting value on the number of fish in the lake. So instead we're going to have to look at the change in the number of fish in the lake. That's a really subtle point. You may or may not be able to get away with this on the exam, but what I know is this. If I just say, let's look at the integral from 0 to 0 of e of t, the rate at which fish enter, minus L of t, the rate at which they leave, well, that's going to be 0. That means that at time 0, there's no change in the number of fish. From 0 to a, if I integrate e of t minus L of t dt, I'm going to get a particular number, and that's going to represent the change in fish population from midnight until t equals a. And then I'm going to do an integral from 0 to 8 of e of t minus L of t dt, and I'm going to look at how many fish we have at that time as well. At this point, we're going to go back over to the calculator. There we go. I'm on the calculate screen, and we're going to say menu, calculus, numerical integral. We integrate from 0 to a. It's e of t, which is f1, minus L of t, which is f2. Integrate that with respect to x, and I'm getting 135.015. Now I want to do that exact same calculation, but rather than integrating from 0 to a, we're going to integrate from 0 to 8. So I'm just going to arrow up and highlight that text, hit enter, and now I can go back and just change my a, change the a to 8, and this time I'm getting 80.920 fish. Let's go back to the screen. Those are all the right numbers. So from time 0 to 0, no change in the number of fish. From 0 to a, I've added 135 fish. From 0 to 8, I've added 80.920 fish. So I'd say the number of fish in the lake is greatest at t equals a hours after midnight. The way they awarded points was they said e of t minus L of t equals 0. So I would say it's this sort of initial work here of identifying where this change in e of t minus L of t happens. Then there's a point for answer, and then there's a point for justification. What I know for a fact is that all of this work here, when you're evaluating the integrals, is your justification. And then this guy down here would count as your answer. So that would be a grand total of 3 points. I want to talk about one other way, and it's a really clever, elegant way that you could do this, but you're going to have to be really specific, really careful with your writing. I'm not going to write the whole thing up, but I will sort of talk you through this. I want to go back to my calculator, and I want to look at the graph. And the graph on this interval from t equals 0 to t equals 8, what I know is in the beginning, and we talked about this, we kind of looked at slices. In the beginning, the number of fish is increasing, and it continues to increase until we get to 6.203, and then the number of fish decreases from 6.203 until the end. That's the only thing that happens. We start off at time t equals 0 with some number of fish, and the number of fish increases until 6.203, so you're getting more and more and more fish, and then you decrease, and you only decrease from 6.2036 until t equals 8. So the number of fish has to be an absolute maximum there. You can skip the analysis of the endpoints. What you're going to have to do, though, is in your writing, explain that you know the number of fish only increases from 0 to 6.203, and then only decreases from 6.203 until t equals 8. Because of that, you have a relative maximum number of fish, and that relative number has to be your absolute maximum number. You guys should all be capable of doing that. But that is the kind of proof that works only in the case where you have one internal candidate. If there had been a second internal candidate, couldn't use that argument. All right, so let's go to part D. In part D, is the rate of change in the number of fish in the lake increasing or decreasing at time t equals 5? I want to be careful here. The question is not a question of is the number of fish increasing or decreasing. That's easy. But is the rate of change of the number of fish increasing or decreasing? And if we're going to talk about the rate of change, that means we're having a conversation about the derivative. So in part D, I'm going to compare e prime of 5, the rate at which the number of fish entering the lake changes, and I'm going to compare L prime of 5, the rate at which the number of fish leaving the lake is changing, and I'm going to compare those two values. So let's take a look. Back to the calculator. This time we're on the calculate screen, and I want to find the derivative, not by hand. I'm going to use my calculator. So I go to calculus, I go to derivative. I want to find the derivative at time t equals 5 of f1 of x. And I'm getting negative 6.802. I can do my copy paste trick again. I'm going to arrow up, highlight the text that I want, hit enter. And now it's f2 of x. That is 3.921. And if I look at e prime of 5 minus L prime of 5, so this expression here, e prime of 5 minus L prime of 5, got an error there, e prime of 5 minus this guy here should give me a negative number. I wonder what. Not sure why that's happening there, but a negative number minus this negative number is going to be negative. So e prime of 5 minus L prime of 5 is negative. Therefore, the rate at which the number of fish in the lake changes is decreasing at t equals 5. So it was 1 point for this analysis, 1 point for the conclusion, for a grand total of 2 points. Not bad, my friends. That is the first of 6 problems we're going to be looking at over the course of the next couple of days.